Okay, so next speaker is Alia Armoni, who's going to talk about QCD, QCD and String Theory.
Okay, thank you very much. This is a work in progress with the Sugimoto. So, but I want to dedicate this talk to the memory of Yitzhak Frishman. He wasn't my supervisor, he was Ami's supervisor, but I worked with him intensively while I was a PhD student. I published 5 papers with him, and he helped me a lot, and I owe him. So my talk today is related to the work I did with him 30 years ago. So the talk is about the 2D QCD, the Toft model. And what Toft did 50 years ago is amazing. He solves 2D QCD in the larger limit. And the solution is a beautiful solution. It moves confinement in 2 dimensions. The spectrum is a spectrum of a radial trajectory, as we expect in 4 dimensions. So it's a manifestation of confinement and chiral symmetry breaking, where the mass of the quarks is 0. We have a massless spiral, so really beautiful. It shares similarities from what we expected for the QCD, but there is also one important difference. So what we have here is just one single radial trajectory. There are no daughter trajectories. So we just have this spectrum without hydrogen density of states, and that will be important for the string that I'm trying to find. So the idea is the following: we have a solution of a model, an expanding solution of a large n 2D QCD, and we expect to have a string dual or a string description of the model, a worksheet description of the model. And interestingly, despite attempts for 50 years and most important, a paper by Strominger, which I would say did a significant step towards the worksheet theory, there is no really a worksheet theory describing this model. And I think that we actually know the solution. So what I will present is a sketch of the idea, because it's a work in progress and I have only 15 minutes, now less. So that's so what is the idea? So the idea is the following: we have the precise solution, and we want to reconstruct the worksheet theory. So the technique was to go through the word line formalism. So what we want is to take standard field theory and re-express or rederive the solution of the model using the word line formalism. So the way that, let me sketch the idea. What we'll have is, let's say, a left quark, a right anti-quark. They exchange gluons. So that's the word line description. I will show, of course, the equations, the formalism. This is just a picture. And as the gluons become dense, we will obtain a string worksheet. So that's similar to what we, the intuition in 4 dimensions, that the gluons make some sort of a fishnet, and as the fishnet becomes dense, we acquire the string worksheet. That's the relation between gauge theories and string theory. So we want to find this worksheet theory. So that is the most important and the most dense slide. So let me explain what's going on. It's not a rigorous derivation, it's just a sketch of the idea. So this is the action of 2D QCD. The interesting or the important thing is that in this light cone gauge, the gluons, it's just a quadratic theory. So we have fermions coupled to the gluons, but it's really quadratic. So that's the essence of why this model is exactly solvable, because it's easy. So what we do, we use the wordline formalism. In the wordline formalism, we can swap or rewrite the fermions as particles. So this is the wordline formalism. Instead of having the quark anti-quark as fields, I write them as particles. It's rigorous. I can show the equivalent.
But how do you encode the spin?
Oh, very good. So what I wrote is just the bosonic part, right? This is for scalar quarks. And indeed, for spinorial quarks, I need wordline fermions. And in fact, the wordline happens to be supersymmetric. So that's interesting.
I suppose that by spin you refer to the statistics, not to the spin, right?
Well, yeah. I mean, Grassmannian variables and yeah. When you swap them, you get the minus. Yes. So I wrote just the bosonic part. I will, if I have time. So I'm sketching the idea. I have only 15 minutes. How much do I have now?
You have
I have 20 more minutes.
I will give the warning in 3 minutes.
Which morning?
You have 7 minutes. 7 minutes.
Okay. So I wasted half of my time. The thing is, so this is why I cannot provide all the details, but I will try as much as possible in the last slide. So I have left particle, right particle, let's say quark anti-quark. This is the interaction. So it's essentially a Wilson loop. So the gauge field interacts with the left and the right particles. And that's the gauge field, the same. I didn't change anything in the gauge field. But upon integrating the gauge field, this is what I get. So I have the left quark, the right anti-quark. And now we see that we have a linear potential between them, which means a string. So we're almost there. That's the idea, that we have quark anti-quark and a string stretch between them. So, and the Hamiltonian of the system is this. So if we look at this Lagrangian, we write the Hamiltonian, that's the Hamiltonian. Okay? So again, the part of this is the light cone Hamiltonian. So quark anti-quark with their masses and a linear potential between them. Okay. Now let's see what is the relation between this new derivation and solution of Toft. Well, if I just write a Schrödinger equation, I get this famous Toft equation. So this is from Toft paper from 50 years ago. And the eigenvalues are what I quoted in the first slide or second slide. So we find the same spectrum, and it's a new derivation. It's a derivation of the solution of the Toft model using the wordline formalism. Now, why is it useful? First of all, it gives us the intuition of a quark anti-quark with a string between them, but we can really do better than that. We can start from this action, and we can rewrite it as a string. So this is our proposal, or at least the bosonic piece of the proposal. This is the proposal written as a Nabu-Goto kind of action. So what we see is that the topology is the disk. We have the disk. On the boundary of this disk, we have the massive quarks. So it's not a CFT. We have a mass here. And we have just a Nabu-Goto action. That's it. And the reason is that this delta x is the integral of the sigma dx the sigma. So in this gauge x minus plus equals 1, this 2D string gives me the solution of the Toff model. So that's my worldsheet theory. That's our worldsheet theory. It's not a CFT. It is a string. It has a particle part. It has a stringy part. The string has this. This is the string tensional to QC. Okay, so now I arrive to the things that I haven't discussed, and David is in the details. And this is the list of the really hard questions and issues that I haven't discussed, that are very important, and we more or less know the answer to these questions. We don't know the answer to all these questions, but we sort of know what's going on. So the first question is that, first of all, we need to add word-line fermions, otherwise we have a scalar quarks. But we know how to do it. That's kind of standard. So we just, and the word-line theory is supersymmetric, which suggests that if you want to have fermionic quarks, and that's what we want indeed, is that we'll have n equal 1 worldsheet supersymmetry. So that's what we need. So the proposal is a two-dimensional string, and with n equal 1 supersymmetry. Now, an important question is how to write the Polyakov action for this two-dimensional string. And again, I think that we know what to do. And then there is an interesting question, the Liouville mode. So the Liouville mode in holography is identified with the holographic direction. Now, from the spectrum of this model, we don't expect a Liouville mode. And why? We don't have the Hagedorn density of states. Hagedorn density of states is expected from, let's say, a 3D string where the string worldsheet fluctuates. That will lead to a Hagedorn density of states. But the spectrum is not like that. It's a spectrum without an exponential increase in the degeneracy that suggests that the worldsheet does not fluctuate. So it's really a two-dimensional string. So then the question is what to do with the Liouville mode. So, and the answer is that I'm not sure that I know the answer. Naively, there is a Liouville mode, but we think that it decouples, at least in a certain gauge.
Is it super Liouville or regular?
Everything is supersymmetric, as n equal 1. Another thing that I didn't discuss at all, and there is a parallel work by Ofer Aharoni, again, work in progress, where he tries to solve this model in a different approach, and his focus is about faults. We don't address the issue of the faults. We believe that in the light-on gauge, it's not an issue, but we have to address it, and we don't, not yet. An interesting thing is what to do with a case with scalar quarks. It turns out that if you do scalar quarks, the field theory is more complicated. The solution of the Toff model for scalar quarks is more complicated than. Actually, I have an intuition for that. With fermions, you have chiral symmetry. With scalars, you don't have chiral symmetry, and that's why it turns out that you have like corrections, and it becomes a bit messy with scalar quarks. So, but I think that the string solution will be actually simpler in the case of the, and I expect just a bosonic string. So to summarize, I think that we will end up with two new string theories, two-dimensional string theories, one bosonic, which will describe the scalar theory, and a superstring with n equal 1 supersymmetry in 2D that will describe the Toff model with the fermionic course. So this is roughly our proposal. Okay, so thank you.